Alright guys, so this is our acid-base crash course. This one's probably going to be a lengthy one, so I apologize. So starting off, we need to know a lot of definitions. So Bronsted-Lowry is the definition that we rely on most for acid-base. There is an Arrhenius definition, there's a Lewis acid and Lewis base definition. However, we stick with Bronsted-Lowry for most of AP. A Bronsted-Lowry acid donates the proton, so it gives off the H+. The base is the one that accepts that H+, so it's accepting the proton. You also need to know and be able to pick apart your conjugate acid and conjugate base. So for instance, if I have acid HA and it's reacting with water, what's going to happen is this HA is going to act as the acid. Water, in this case, is going to act as the base. So the HA, the acid is going to give an H+, and the base is going to accept that H+. So your products for this reaction is going to be H3O+, which is the hydronium ion, plus A-. When your acid has given off the H+, this is what you have left over. This is known as your conjugate base. When your base has accepted the H+, this is what you have as your product, and that's known as your conjugate acid. Some other definitions are amphiprotic or amphoteric. That is things that can act as an acid or a base. So for example, water can act as an acid or a base because he can receive the H+, which is what we witnessed right here in this example, or he can give off an H+, to have OH- being as a product there. So amphoteric or amphiprotic means that it can act as both an acid or a base, but it's only going to be one or the other in a particular equation. Monoprotic means that an acid, you have only one proton to donate. So HA would be an example of that. It only has one hydrogen to give. Diprotic means you have two protons that you can donate. An example is H2SO4. So you have two hydrogens you can give. And polyprotic has three or more. I should have written 3 or more protons to donate. So H3PO4, phosphoric acid, that has 3 protons that it can give. There are also polyprotic bases. Polyprotic bases are things that have multiple negative charges, so they can receive lots of hydrogens. An example is PO43-. PO43-. PO43- can actually accept 3 hydrogens and to make H3PO4, so this would be a polyprotic base. The next thing is just knowing about strong acids and strong bases. Remember that strong acids dissociate completely in water. So you have all of your molarity, all of your concentration of the acid you're starting with that is transferring into H+ ions. It dissociates 100%. The same thing happens with a base, strong base. When I am trying to find the pH of strong acids or strong bases, I find it by pH is equal to negative log of my H+ concentration. This is what I use if I have a strong acid. I directly plug in the molarity of the strong acid right here for its H+ concentration. The reason why I do that is because it dissociates 100%. If I have a strong base, I first have to find the pOH by negative log of OH concentration, and then once I find that pOH, I use pH plus pOH is equal to 14 to solve for the pH right here. So that's how you work with the strong bases. Remember that if you have an H+ concentration, then you take the negative log of that, or if you have the OH concentration, you take the negative log. But if you're trying to find an H+ concentration, you take 10 raised to the negative pH to find that. If you are trying to find an OH concentration, you take 10 raised to the negative pOH to do that. And if you have an H plus concentration and you're trying to find an OH concentration, then you use your Kw expression to be able to find that. And we're going to talk more about Kw in just a minute. For weak acids and weak bases, then we do not have 100% dissociation. Your dissociation ranges between 1 and 3%. It's very, very low. So how we work with that is you get Ka and Kb values. For weak acids, your Ka expression is basically your H plus concentration times your A minus concentration over the acid concentration overall. Remember that you don't include water because you never include pure solids or pure liquids in your K expressions. For a weak base, your Kb is going to be your Hb plus, so when that's basically your conjugate acid here, times OH minus, and then you divide by the concentration of the base that you started out with. To figure out the pH, you have to do your Rice charts. And so there's an example right here of your Rice chart. So you would set up your Ka expression. And remember that you can neglect this x right here. But you have to show that you are neglecting that x when you're showing work. For Kb, it's the same setup, the same expression, and you also get to neglect that x. But you do have to show to the AP reader that you know that you can neglect it. When you do your Rice chart, you're solving for x, which is the H plus concentration. After you know the H plus concentration, you then can stick it into this pH equals negative log of H plus formula to find the pH. If you're working for a weak base, you're solving for x to figure out the OH concentration. Once you know the OH concentration, you find the POH and then use this last equation to find the pH from there. There's also something known as percent dissociation. You usually do this with your weak acids because you don't know how much of that is actually dissociating. So another equation, percent dissociation, is equal to the concentration of your H plus divided by the concentration of the acid that you started out with. And then to make it a percentage, you multiply by 100. The next thing I want to talk about is your oxyacids. This is an essay type question where you have to justify what you're doing. So this is an essay based question. As you increase the number of oxygens, the strength of the acid increases. So that's the concept, but you have to be able to justify why that is the case. So an example would be that you have HClO3 versus HClO4. HClO4 is one of our strong acids. Don't forget, I haven't mentioned this earlier, but don't forget to know your strong acids and strong bases. So look back in your notes. There's 6 strong acids you have to memorize. That's HCl, HBr, HI, HClO4, H2SO4, and HNO3. You also have to memorize your strong bases, which are basically the first column, your group 1, so that's like sodium, lithium, all of those down with an OH, and your second column except for Be and Mg. Right, so the first column in the periodic table and the second column with an exception of Be and Mg, those are your strong bases. Anything else that they give you is considered a weak acid or a weak base. And also don't forget that NH3 is a weak base. A lot of students forget that. So sorry I went off on that tangent, but back to these oxyacids. So HClO4 is a stronger acid than HClO3. Now our justification as to why is not just that as you increase oxygens, you increase the strength of the acid. Our justification lies within this process. So oxygen is electronegative, so it attracts the electrons away from the OH bond. As more oxygens are added, the electron density increases. So what that means is that the electrons are being shifted further away from that bond that you have between the O and the H. As the electron density increases, the OH bond weakens. So if the electrons are shifting to the other side, that bond there is being weakened. If the bond weakens, then less energy is required to break it. And the whole definition of a strong acid or a strong base is basically how much it dissociates. So if it's more easily dissociated, if it dissociates more readily, then that means you have a stronger acid. So that would be your justification. You need to include all of that within your reasoning for a free response question. The next thing is KW. So don't forget your KW equations. It's equal to your H plus or your H3O plus concentration times your OH concentration. And KW at 25 degrees Celsius is always equal to 1 times 10 to the negative 14th. Because K is temperature dependent, if my temperature increases, that's this expression right here, if my temperature increases, my KW increases as well. What I can do with KW is solve for my H plus and my OH concentration, and when I do so, I can compare those values to tell if the solution is acidic, basic, or neutral. So if I have more H plus, then that solution is acidic. If I have more OH, that solution is basic, and if those are equal, then I have a neutral solution there. Another equation for KW is to convert between Ka and Kb. So Kw is equal to Ka times Kb. So if I have an acid, but they give me a Kb value, then I have to convert to Ka to use it for acids. Kas can only be used for acids, and Kbs can only be used for bases. Now let's look at salts. So you have acidic salts, basic salts, and neutral salts. An acidic salt is formed from a strong acid and a weak base. So an example would be a strong acid and a weak base. So let's say NH4Cl. NH4 came from NH4OH, which is weak. Cl came from HCl, which is a strong acid. So this would be an acidic salt here. Basic salts are formed from strong bases and weak acids. So an example would be Na, let's say 2CO3. Na came from NaOH, and CO3 came from H2CO3. NaOH is a strong base, H2CO3 is a weak acid, so this would be a basic salt. Neutral salts are formed from both a strong acid and a strong base. So NaCl, that comes from HCl, which is strong, NaOH, which is strong as well, so this would be a neutral salt. When you work with salts, you have to be able to write a hydrolysis reaction. Hydrolysis reactions are where you say that your spectator is whatever is strong. Alright, so I'm going to work with this basic salt here and write my hydrolysis reaction. Because Na was my strong thing, this is going to be my spectator. So I'm going to start with CO3 2-. When I have hydrolysis reactions, water is your reactant. Hydrolysis means splitting of water, so think of water as HOH. Since this carbonate is a negative charge, the H is going to bind with that because positive and negatives get together. So I'm going to have H2CO3 plus OH minus. Now, it makes sense that OH minus is going to be produced here because it is a basic salt. So this would be my hydrolysis reaction. In order to find the pH of a salt, I basically set up my rice chart. So let's say that my concentration was 0.5 of this Na2CO3. So I would start with 0.5. Water doesn't get included, so this would start out at 0, 0. And in this case, I would solve, this is plus x, minus x. I use a Kb expression to solve for x, and x is my OH concentration, so that's what I'm looking for. Since I'm solving for OH, I would have to find a pOH first, and then a pH from there. If I'm working with an acidic salt, then I'm going to have H pluses as my product, so I would use a Ka value, or Ka expression, and then from there I would find H plus, which is X, and then solve for pH by plugging it directly in. If I have a neutral salt, that pH is always going to be 7, so that's pretty easy. Now the next thing we need to talk about is buffers. So when you're working with buffers, okay, so when I'm working with buffers, what makes a buffer is a weak acid and its conjugate base, or a weak base and its conjugate acids. When you're reading through these questions, anytime you see ic, like something ic, and 8, that automatically signifies that you have a buffer there. We'll talk about the buffer region in our titration curves in just a minute. So the equation that we use for buffers, and this is on your equation sheet, is pH is equal to pKa plus log of A minus over HA. So don't forget what A minus and HA are. A minus is your base component, which would be, if this is a weak acid conjugate base, it would be your conjugate base concentration. Your HA would be your acid component. So this is your acid component. Remember that pKa is just negative log of Ka. So that is how I find the pH of a buffer. Now remember that if I add a strong acid or a strong base to a buffer, what that's going to do is resist a change in the pH. How it's going to do that is by, if, let's say for instance, I had a weak acid and a conjugate base in a buffer, and I add a strong acid, the conjugate base component is what's going to neutralize this strong acid that comes in. If I have a weak acid and conjugate base component and a strong base comes in to the system, then this weak acid component is going to neutralize that strong base, so the pH will not change. So what you have to be able to do is write your reactions between these if you have a strong acid or a strong base entering. So one way that I would do that is, in this case, my conjugate base is what's reacting with my strong acid, which is H pluses. So then I would just finish up my equation from there. And then I would set up a Rice chart, or just do M1V1 equals M2V2 and then go from there. If I have my weak acid that is going to react, it will be weak acid plus strong base, which is OH minus, and I finish out that equation. And then I could do my new molarities, I could do a Rice chart, and then plug all of that information that you find into this buffer equation. So that's how we work buffers. The next thing we need to know is choosing the correct indicator. So there's two ways you can do that. either the pH range for the color change, so the color change of the indicator, must equal the equivalence point pH range. So if I have an equivalence point pH range that's going to be between 8 and 10, so that's when my equivalence point has been met, then I want to choose an indicator that has that color change range between them. The second way you can choose your correct indicator is by saying that the pKa of the indicator is equal to the pH at equivalence point. So if my pH at equivalence point is 9, then I want my pKa value to be 9 as well. Now if you have a Ka value given, you're looking for that 10 to the negative 9, whatever's closest to that value. Now titration curves. Definitely know your titration curves and all of the components that are along the titration. So what we have right here is a titration between a strong acid and a strong base. How I know that is I look at the beginning pH. So that indicates what my analyte is. So the beginning pH is for my analyte. And if you remember back from lab, our analyte is what's in the flask, and our titrant is what goes in the burette. So this is our titrant, and this is our analyte. So the strong acid in this case is our analyte, and a strong base is our titrant. The reason why we know that is because the pH starts really low and the pH ends very high. When you have a strong acid, strong base reaction, then my equivalence point is going to be exactly at 7. So the beginning pH is the analyte, the ending pH tells you who the titrant is. If I look at this second graph for my titration curve, my beginning pH starts very high, my ending pH starts very low, and my equivalence point is at 7. So this means that I have a strong base as my analyte and a strong acid as my titrant. My equivalence point is at 7, so that tells me that I have a strong titration. Now let's look at this titration curve to the right. My beginning pH is starting a little bit higher, but it's still in the acidic range, and my ending pH is starting at a very high range for bases. So this means that my weak acid is my analyte, and my titrant is a strong base. For weak acid, strong base titrations, your pH at the equivalence point is going to be greater than 7. So pH at equivalence point is greater than 7. Also, we need to be able to label the other components here. So I have at the beginning just my weak acid. This range right here is very important. This is your buffer range. And we can tell that because it's resisting a change in pH. We're going to label the different sections that you have in just a minute, like when your weak acid is greater in concentration on all of that. But right now you need to know that that is your buffer range. Let's look at this last titration curve. We have our pH starting out at a basic pH, but it's not very high, and we have our titration ending at a very low pH. So this means we have a weak base as our analyte, and we have a strong acid as our titrant. The equivalence point for this case has a pH that is less than 7. This right here would be my buffer range because it's resisting a pH change. Now let's look at those titration calculations. So I want to label this. So A is the very first point, all right? You have B, which would be after A. Let's look at C. That would be C at that point. D would be at this point. E would be here. And F would be in this range here. Okay, so looking at A is when you have only a weak acid present. So when you are trying to find the pH for that point, you're going to use the weak acid approach that we talked about earlier. Remember that your buffer range is in this part right here. So this is our buffer range, or our buffer region. For part B, I have more weak acid than I do my conjugate base. They love to ask questions about these relationships. I have more weak acid than my conjugate base, and I have a buffer there. So I'm going to find my pH at that point by using my buffer equation. Point C is very important. It's known as the midpoint. How I find my midpoint is by looking at this volume at the equivalence point, and when I see that volume at equivalence point, I take half of that volume. So half of 25 is 12.5, and let's just say that it is centimeters cubed because that's what our units are right here. So I have 12.5 centimeters cubed. I look at the pH right there, and that is my pH at midpoint. At midpoint, I have the best buffer ratio. The best buffer ratio is a 1-to-1 ratio of my weak acid to my conjugate base. Or if I had a weak base conjugate acid, it would also be a 1-to-1 ratio. So, because these ratios are equal, to find the pH at midpoint, I just say pH is equal to pKa. The reason for that is because this section, log of base over acid, this is a 1-to-1 relationship. So the log of 1 is 0. So that's why we say that pH is equal to pKa. Sometimes they have you find the Ka expression from this titration curve. So you would look at the pH at C, and then you would plug it in to solve for Ka. For section D, you have more conjugate base than you do your weak acid. That's an important concept. So you're getting more and more of your weak acid depleted as you go along after the midpoint. At part E, all you have there is your conjugate base. You have totally gotten rid of all of your weak acid that you started out with. And at the equivalence point, your moles of your titrant that you've added is equal to the moles of the analyte that you started with. When you have your conjugate base only, that is known as your salt. So to find the pH there, you're going to use your salt approach for pHs. If I've gone beyond the equivalence point, now I have OHs that are free floating around in there. Not only do I have the OHs, but I still have the conjugate base that I created at my equivalence point. So to figure out the pH there, I'm going to basically do a limiting reactant problem to solve for how much of this OH that I have, and then plug it into my pOH formula.